Hey everyone, welcome back to the lab. In this video, we're going to be talking about why type-safe programming languages are better than dynamic and lead to faster, safer software at scale. So type-safe programming languages are better than dynamic for building and maintaining software, especially at scale. This is a perpetual point of contention in the software community, but it really shouldn't be. Type-safe languages scale and dynamic languages don't for the most common and impactful bottleneck in software, the humans building it. In this post, we'll explore the differences between type-safe and dynamic programming languages and how they scale through the lens of a metaphor, wire management. So first we need to establish a little bit of context on the foundation of the metaphor we're going to be using throughout this post. And that metaphor is one for control flows as wires. So to explain how type-safe and dynamic languages work in the real world, we're going to use a metaphor that hopefully most people have dealt with before, and that is wire management. And so first, I'm just going to posit that you can represent a program as a series of wires. And so let's say we've got like, a dumb little pseudocode definition, and it's like a wire, and then it takes in a payload. And then, based on some conditions, it decides it could split the payload, which it could send it somewhere else. And maybe it only sends it there, or maybe it continues and it also goes forward through the control flow. This is how we kind of do control flow in programs. And we can basically represent that with just some arrows, right? So the continue would be this one, the split would be this one, and obviously a lot of different ways to put these together where maybe you only go this way or maybe you go down. But basically we can model the same kind of programming control flows we have as wires in the form of these, directional arrows. And so each of these wires is going to represent a control flow from one function to the next. And then the thing that's going through the wire is, the function it would go through as data. Through the wire in our metaphor, we might say it's a payload, which can be anything, but we'll talk about that in a second. Okay, and for our own sanity, we are going to assume that the data only moves through a wire or control flow in one direction. This is like mostly true in both domains from a very high level. If you squint, if you look at like a system architecture or you look at a program system design, if you squint, really things do only move in one direction. But obviously, if you go deep into the weeds, that's not true. But because this, at a high level works, it's going to save us a lot of complex edges that will cause this metaphor to break down and desync. And so this is just going to make it work. As a sanity check, factory games like Satisfactory, Mindustry, and Factorio, all of these really only do one-way traversals, but it still serves as like a pretty good parallel to programming and data flow. And so if those can do it at their scale, we can probably do it at our much smaller scale for this metaphor. Okay, and so what this means is that in our metaphor, a wire is going to represent data and control flows in a program. And so from a program's perspective, a control flow carries data, and this data is going to move in one direction, and it might split into additional flows. It goes from one to the other through like mostly variables, let's say, and function calls. And that data can really be anything, like in the same way that you can say that this function takes in a list, but that list could be like, hundreds of thousands of lines long, or you can say that this, function takes in this object, and that object is just like a ginormous blob of something. And we're just going to say that data can kind of be anything within reason. And because you have, control of these variables, you can pass like whatever shape you want as well as that size. The next thing I want to point out is that you cannot actually discern what data is flowing through a control flow without additional info or context about that flow. And so kind of what I'm talking about here is like when we're writing code, if we have a dynamic language and we write a variable, let's say Python, if you're not using types, and I say my value, my variable, or something, and I use that as an argument to a function, there's no way to discern what my variable is without extra context. And so extra context would be like adding the optional types. It would be like seeing where that function is used and tracing back to where the data comes from to figure out the type. You need extra info to understand. You can't like get IntelliSense or anything at any given point that will just tell you because there's not enough context for it to understand that. Hopefully that makes sense for dynamic languages. Obviously not true for type-safe languages, which is, the whole point that we'll get into as we go. Okay, and so this is the like program perspective. And so now let's look at the wire perspective, which is going to mirror this. And so a wire is going to carry payloads, so it's just data. This is payloads, can be anything. And it also moves in one direction and may also split into additional wires. Similar to data, a payload can be anything within reason, because programming can do any shape or size. So we're going to say it can be any shape or size. And similarly, you cannot discern what payload flows through the wire without additional info and context about the wire. And so this is like, here, I have a bunch of wires on my desk. I have this wire. Me showing you this, if you're not looking at the ends, you have no idea what this wire is. Like, is this an aux cord? Is this a power cord? You don't know. And so this is very similar to that idea of dynamic variables, where if there's no additional context, you just know it's a variable, but you can't actually check what that thing is at any given point. Similar to here, in the middle of this wire, me showing you this, you feeling this, you don't know what it is until you look at the ends and know where that data is coming from to actually know for sure. And here, it's an aux cord, so it'd be aux. Hopefully that makes sense. Okay, final thing about setting up kind of this fantasy wire world that we're going to be playing within is that there is a known limitation with this. And the biggest issue with this metaphor is that, wires are in real life. And when we think about wires, they're mostly static. It's just a thing, you plug it in, it stays there. And so you set it once and then you use it a lot. The problem with this, and really most metaphors that deal with software to the real world, is that software is mostly changing like all the time. Like we're changing foundations, we're changing the color of the walls, we're changing what the electronics in this room are made out of. Like everything's kind of able to be changed, and so it is. And so this is where it kind of breaks from our lived intuition. And I'm going to try to point this out as we go. But I do want to keep it in mind that, modeling software dev like as a building in real life is akin to that building like being constantly under renovation. Like that doesn't really happen in the real world because that'd be like ludicrous. But in software, that is what we're doing. We're always renovating the building. If our software is the building, it's always being renovated. Everything's being touched. Nothing is safe from change. So that's the biggest limitation. I wanted to call that out here. And I will remind you as we go. Okay, so now that we understand that wires and programming have parallels in the kind of area of the metaphor that we're going to be playing in, now let's talk about type safe versus dynamic wires. So recall that like all wires look and feel exactly the same in our fantasy world. So this raises some obvious issues, like how do we ensure we don't cross our wires when we're wiring, whatever thing we're building? Now this is the core issue at play between dynamic and type safe languages, so this is a good question to keep in mind. And before we go into scenarios, I first want to point out a few common strategies each uses to avoid the crossing of wires. So we have some shared context about that, because I think it's going to help when we go into the scenarios to go kind of faster and on the same page. And so when I think about the difference between dynamic and type safe wires, really it comes down to this. Dynamic wires all look and feel exactly the same. It is very hard to understand what that thing is in the middle. You kind of have to go to the source to figure it out because there's just no additional context helping you because it's dynamic. Type safe wires. And when I say type safe, static typing does this, but really strict typing does this. There's a lot of really great algorithms that allow you to have type safety without necessarily going full blown like Java define and declare everything. But really we're focused on type safety, which basically says, this is a blue wire, it only accepts blue things. This is a green wire, it only accepts green things. This is a red wire, it only accepts red things. And from there, that means at any point when you see this wire, you know what that thing accepts and therefore what it doesn't. And that's really, the difference. And so when we talk about dynamic wires, each wire looks exactly the same, has the same color, the same connectors, the same feel. And so this means you could connect a wire carrying electricity to one carrying water, which is bad, because there's nothing stopping you or often even warning you from doing such a thing. And so like the most common version of this, right, is like you pass a null into a thing that thinks it's not null and you get the null pointer exception, right? Like that's like the most common error probably in programming. And it's more or less the same as like passing electricity to water in our wire world, and that it causes things to blow up because you did the wrong thing in the wrong wire and nothing stopped you. And so when you think about dynamic programming languages, what are ways that they try to avoid this like catastrophic wire crossing? And the first thing that they do is you like double check the things before you're using it. So you might turn the wire on and see what comes out in the wire version. Is this electricity? Is this water? And in programming, this is more like maybe I'll run I'll spin this up in a dev environment and I'll play with it to see what comes out. Maybe I'll have some logs to see what's actually going through this thing. That's kind of like double checking what it is before you use it. The next is like utilizing automated tests to detect if a change breaks something. This is like the most common one I see, where you've got unit tests and you're like ensuring that does this flow work? And so theoretically, you know, if it works, the wires are connected correctly. There's not really like a wire world like in real life equivalent to this. Like we don't really have a way to clone the world and like test it through different scenarios. But you could imagine if there was like a button in the basement of an apartment building you could press and it would like turn some TVs on and off and make sure they go on and off. It would flush some toilets. It would do some stuff like that. That's kind of what this would be. And it mostly works, but you could obviously imagine you have to test all the toilets, you have to test all the TVs, and it's easy to miss a few. But this is kind of how that works here. The next one is to build type guards into usages. And so this is kind of like null checks. I think null checks is probably the one we're most used to, is like at the top of functions, if you know something could be null, but you don't want to deal with null, you're like, if my variable is null, return. That's a type guard, where you are preventing the bad thing from entering you by checking everything that comes in. And so the wire equivalent of this would be like, let's say like every wire has like a switch breaker in it that will turn itself off if it's something that it doesn't expect. So like, you know, a lot of new phones now, if it's like submerged in water, it's going to turn off the ability to charge for a while until it knows that there's no water in there because it's protecting itself from shorting out. Like imagine a wire has that. That's what the equivalent would be in wire world. And then the final thing, and honestly, this is often the first thing that people try, is they try to add descriptive variable names and then dot comments on it. And so this is like a sticky note or a label from a label maker on stuff. So like, you know, this wire right here, if it was much longer or was plugged into stuff, I could, you know, put a little piece of paper on it that says this is an aux cord for whatever headphone. Like that's one way that people try to keep things from entering or not. Or another one is like, in a lot of houses, you have like a lot of light switches around, and there's like sometimes a few switches that either do nothing or it seems like they do nothing, but actually it's really important. Like it turns off the gas, or it like, if this one's off, then none of the lights in the living room work or something like that. And so you have to like label them. You're like, do not touch this ever, or whatever. Like that's what these things do. And so we're going to be using these a bit as we go on. But I wanted to share like the ways dynamic wires try to approximate safety, because I think it's important to understand what you're gaining in other contexts. So what are those other contexts? And really the alternative is to use type safe wires from the jump. Okay, and so I told you that all wires in wireland do look and feel exactly the same, but I never said one couldn't upgrade wires to allow for additional info and context on them. And this is essentially what type safe wires do. And honestly, this is basically the exact same thing that typed languages do and that dynamic languages don't. And so it's a really good parallel. And so we're going to say that like each type safe wire can be color coded. So instead of those, you know, black lines I showed you earlier, instead of the black lines that we get with dynamic wires, we can have all sorts of colored type safe wires. And the programming equivalent of this is like, you know, in wireland, if I were to connect a red and a green wire, it's like, why is that not the same color? That looks suspicious. And, you know, in this case, it wouldn't even connect because you can't do that. But in the programming thing, if you were to do that, you would, for the most part, assuming your language has a good language server, it's going to throw red and yellow squigglies, and it's going to be like, hey, this looks weird. Like, I don't like what you're doing. Either fix it or tell me that you know what you're doing and you want to disregard my warnings. You know, it gets very mad when you do that. It's very obvious that you just did something that's not great. The next thing that these type safe wires give us is that connectors can have different shapes, and this makes it impossible to directly connect wires of incompatible kinds, though you could, of course, build an adapter. So, you know, my red and green, like, they can't go together. Like, they're not the same kind, so they can't go together from the first place. I won't even get my squigglies. I can't do them together. But if I figure out a way that I can convert red to green or whatever it is, then I can build that adapter and do it, and it will let me do that because I have an adapter. And the programming equivalent of this, of course, is compile errors. It's not going to let you connect these things unless you figure out a way to convince it that this can be casted or changed into this other thing through the code you've written. And the last thing, and I think this one is crucial, is that it's easy to see exactly what this wire is made for. Now, it's hard to figure out like how this would actually work in in the real world, but we could assume that maybe there's like a built-in display on the wire that tells you exactly what it is, or maybe there's like some sort of QR code that gets updated that lets you know what's in the wire. Or maybe, I don't know, there's like a label that just somehow automatically updates. And this is in the form of IntelliSense. And so I was showing you earlier how, like, you know, in dynamic programming languages, we have my variable. I have no context when I see that variable what that is without going and finding it. With type-safe languages, even if you don't declare often what that thing is at the call site, the compiler, the language server, can figure that out for you. And so at any point when I see a red wire, I can just say, what's in this red wire? And it will tell me exactly what is in this. Is this electricity? How much electricity is it supposed to be? Is this water? Is this sewage waste? What's in this wire? And I can figure it out anywhere. So if I'm digging through a hole and I find the wire, what's in there? Can I cut that? Can I not cut that? That's what we get. And we get that through IntelliSense that comes from language servers and all the tooling we get, you know, and with our development environment. Okay, so after reading these descriptions, you might say, hey, this is unrealistic. This is not a very fair comparison of dynamic to type-safe languages. It's not fair to say that dynamic languages have to deal with impossible to differentiate pipes, or wires in this case, while type-safe languages get color-coded pipes. And I would say back, yes, this is not a fair competition. One is clearly better than the other. And yet here we are, once again, explaining this because people keep using the bad one in production. And so now the basis of the metaphor and my argument, let's get onto some scenarios. Okay, so the first scenario is going to be very simple. We're just going to be wiring up a desk. And so when you think about the number of wires, they're on the order of like 10 wires maybe. There's probably only one person working on this. So it's like a personal desk. And the changes per day is probably just one. And so the programming equivalent of a desk of this size, of this complexity with this much wires is going to be a very small software project or prototype that you built yourself. So probably like a side project, or if this is at work, it might be like an internal little tool that you like tweak, you know, every now and then. It's very small. You're the only one working on it, so nobody else is introducing changes, and you understand the whole thing. And so let's say for this, we've just got like a pretty standard software engineering desk we need to wire. So we got like a laptop, we got 2 monitors, and we have like a mouse and keyboard. So this is going to net us with like a pretty manageable 7 wires. And so let's pretend we go and we plug it all in and then we kind of see what the results look like. And so this is what the results are, right? We got our accessories, they plug into our laptop. We've got our power that's going to like our monitor 2, our monitor 1, and our laptop. And then we've got our laptop using, video outputs coming out here. And so using dynamic wires, which I'm, showing in black because we only have black in our dynamic wire metaphor, is pretty easy to do, Like this is like wiring your own desk without cable management. You've probably done this before. And with this many wires, we might have a bit of a wire ball behind the desk and it might not look the prettiest, but like it's still pretty easy to move and switch out if you need to, like one of your wires isn't working or you're getting a new monitor with a new connection or something like that. It just might take you a few minutes to like find the wire that you need to pull out of the ball, kind of trace to where it goes and, unwind it and get it out. So not too bad. And here's the kind of type safe version, the ones that have the different kinds of inputs, outputs are going to be, different colored. So it's just easier to see what's going on. And so type safe wires is a lot like using cable management from the jump. It probably took you a little longer to set up because, you had to make sure you had the right kinds of wires. Do I have enough of the power wires? Do I have enough of the video wires? Do I have enough of the accessory wires? And then it probably took you some time to bundle and organize them, to pull out the slack, to put them with the little Velcro things, and then to store it nicely behind or under your desk so it doesn't look awful. And so it took longer to get set up initially. But the flip side is that the next time you have to move or update a wire, like you get that new monitor or you get that new accessory that needs the new wire, you know exactly the wire that you need to change and it's not wound up in a ball so you can just unplug it and move it without doing the tracing or without doing the unwinding from the knot of wires. And so in this very simplest scenario, we could say that the outcome here is a draw. Maybe we'll give a slight win for dynamic if we don't have a lot of changes down the line. So we're just going to set it once and forget it. But we might say that type safe gets a little bit of a slight win because if there are more changes, because it's easier to make those changes down the line because we're not doing with the tracing of the wires, we're not dealing with unwinding the balls. And so both perform about the same at this very, very small scale. Type safe wires takes a bit longer to set up. So we could even say that dynamic wires wins in this case for the time to initial setup. But again, I'm going to recall what I kind of warned you about earlier, as is the main downfall of this metaphor, is that software is constantly changing. So this is a desk that is regularly receiving changes about once per day. And when you think about changes in software, there's gonna be like a pull request getting landed or something like that. And so, even at this low change velocity, we won't see too much of a difference, but perhaps the cord management approach that doesn't deal with the tracing and that doesn't deal with the, unbundling of the wire knot still wins at this scale. But for now, we'll say draw. We'll even give a slight win to dynamic because, it needs the points. Okay, let's go up a notch in scale with scenario 2, which is wiring an office floor. So in this scenario, let's say we've got about 1,000 wires. Let's say we've got 10 engineers, and so those 10 engineers are producing about 10 changes per day. And the programming equivalent of this is probably like a single product for like an early stage startup. Like you just got one thing you're working on, and maybe you got like a website and back end, whatever, but it's just like one thing, 10 engineers, relatively small team. And so here in Wire World, we're gonna try to scale up similarly. And to do that, we're going from our desk to like a little office floor that has maybe a few units on it. And each of those units has kind of the core things you'd need in an office. And this is trying to parallel like the core things you might need in a backend. They all are full stack software. They all need basically the same things. They just kind of scale larger. And so for our purposes, what we're going to try to parallel is different kinds of data flowing through our program. And so here we're going to say we need some desks with electricity, and we're going to say it needs electricity. We're going to say maybe each unit needs a small bathroom, so it needs water, sewage, electricity, and then maybe a kitchenette, which needs water, electricity, and honestly probably sewage, but that's beyond the point. And I again want you to, remember that software is constantly changing. So in Wireland, this means that all of these wires are changing too. And so for our metaphor, this offices are being constantly renovated, while they're being used, while they're being worked on, with 10 engineers making about 10 changes each day. And, I don't know what they're doing. They're like breaking down the walls, they're adding wires, they're removing wires, they're changing wires. Like there's no real world's parallel to like why software changes so much, because we can't do that in the real world, but that's like what happens in software. We're constantly renovating everything. And so now that we're in a bit more of a complex wiring scenario, we're starting to get types of wires that should not be crossed. And if they do, bad things happen. And so these are things like maybe you mix the electricity in the water and we get fire. Maybe we mix the sewage with the water and that's just nasty. And then like the programming world, this is like, you are passing in the null when you don't think it's a null. It crashes the whole program. Bad things happen. Or you are making a miscalculation and you are passing it through something. Well, let's just say, all your program's entirely right, but you're just using the wrong pipes, right? You have a correct value, but you pass it in the wrong variable field. Therefore, it's in the wrong pipe. It's saved to the wrong thing, and it breaks the program down the line. That's what we're talking about when we're saying it's causing a bad thing to happen in the building. It's causing a really bad thing to happen in your business. And so we don't want to do the wrong thing, but we also can't stop changing the wires because business, the renovation must go on. Okay, and so here's an image of us wiring an office floor with these dynamic black wires. There's no way for us to know exactly what's in that thing. And so we're kind of like, eyeballing it. We're like, I think this is where the electricity goes. Like, maybe that here's the water, here's the power, here's the sewage, and we're linking all these things. And it can work, but maybe it's a little bit harder as we get to larger scale to get the right things to connect with the right things. And so it's at this scale that we really start to see dynamic wires and languages start to stretch a bit at the seams. Doing what we did at very tiny desk size worked okay, but as we got more engineers changing things all at once, it got harder to remember what wires were doing what, because some might have changed from yesterday. And so a very common example of this is like you build the first version of a piece of software. And so you know exactly how it works. And then you go off to focus on other projects, you get new people on the team, and they start making features and changes or whatever. You might come back to that software that you believe you have a perfect mental model of and try to change it the way that you think it works. And that might be correct based on, your knowledge, but there's so much room for something to have changed from out from under you. Maybe where the water used to be, now it's electricity. Maybe the ways that sewage is, flushed out of your program has changed. And so you have to kind of assume as you come back to a program, where you have many people making changes is that you don't actually know the way that it's fully working because it might have changed out from under you. And so let's assume this is happening. There's hundreds of changes. The wiring's changing, we have all these black wires everywhere. And obviously this is confusing as it is, and it's just a static image. Imagine it's changing so much. Like, it's going to get very confusing, especially in 4 weeks when it like barely resembles what it looks like today. And so how are we going to, deal with this on our team of engineers? So let's say we decide to implement a few things to try and prevent this because, we're crossing the wires, we're getting fires, we're getting nasty stuff just everywhere that's making us sad and our customers sad. So the first thing that inevitably happens in development teams is that they try to tell everyone, what you did yesterday so that people can keep up with what the wire does, what's changed. Basically, we can keep up with a full mental model of the current state of the room. This is like basically what stand-ups often turn into at agile companies and the reason that they stay. And so that's the parallel. The problem is this probably works for less than 1 week. One, because maybe you are giving all the information and so people are just zoning out because you're talking about that side of the building, but you're focused on this side of the building. So it's has nothing to do with you think, until you hit it in 2 months. Or the other way it happens is you're paying attention, but people are leaving out little changes or little details about what they did, so that even when you come back and you remember a change happened, it's not actually up to date or it's been missed. And yeah, in programming world, this is stand-ups, or this is very detailed JIRAs where it's if we just write it all down exactly what happened, then everyone's going to know what happened. And it's nobody's going to read that. Nobody has the time. By the time they read it, it's stale. So this is always the first thing people do. Doesn't work. All right. The next one is to tell all the engineers to check the wire type before we connect them. Because obviously we always check everything before we do anything with it, right? And in general, I think this is a good idea, but usually this requires a bit of time. So how am I going to check what is in this thing? Do I look at logs? Where are those logs? Do I run tests? Okay, the tests look fine, but does that cover all edge cases? Do I run the thing myself? Okay, I'm running it in dev, but I don't have access to production data. Do I run it in prod? Well, that's weird. Maybe I shouldn't be looking at prod data. You should check the thing, but, checking the thing isn't always quite as simple as it says. But let's say we try this. And let's say, again, I don't really know how to check or test in the real world, but maybe you turn on the water thing and make sure water comes out the wire. Maybe you turn on the electricity thing and you plug it into electronic and make sure it lights up or something. And again, this requires some time and effort and wire world. Maybe it's a trip to the basement to turn the water on and off. Maybe it's you broke your little electric thing because it wasn't electricity, whatever it is. And so eventually what's going to start happening is people start cutting corners because it's honestly a lot of work to do this. And you start thinking well, I just tested it last week. Of course it's still electricity. Of course it's still water or whatever it is. But actually you're wrong. At 10 changes a day, you're bound to have at least one breaking change from week to week. And especially it's usually month to month or year to year. And then it just keeps the cycle going. And so you get fire and you get nasty stuff. Bad. You don't want that. So another thing that people are going to try is they're going to add labels to the wires, So if you go through the test and the test takes a long time, how about you just add a label to the wire of what it is? This is electricity now. This is water now. And this works great for a while because people are adding and reading labels to the wires. But the problem with this is you got to start adding lots of labels everywhere because, those labels don't actually flow through your wires, right? It's only a label on the outside of the wire. It's not built into the wire that you can check anywhere. And so the equivalent of this is writing doc strings and stuff on functions and dynamic languages, thinking that will save you. But if someone's 2 levels up or 2 levels down, they get none of that context. And so in wire world, this is every time you see the wire, you got to add a label. But what if I, make a hole in the wall and I see a wire? I don't know what that wire is because there's no label there. And so it's just a lot of work to add labels. But let's say we go with that and it probably works okay for a while. But one day it's going to happen that someone's going to trust that label and it's going to be wrong and there's going to be a fire. Or it's going to, have some nasty stuff. And why did this happen? Because someone must have changed the wire and didn't update the label. Wow, surprise, surprise. And truly this just happens not because of maliciousness, because this is not a scalable way to add context. Comments in code are not tied to any one central source of truth. And so you having to go and trace everywhere your code hits to change all the comments everywhere is just as bad basically as needing to trace the code to figure out what's in the wire. It's too hard to do the tracing, and thus it's going to be too hard to keep everything updated. And so what ends up happening is people try the dot comments thing, they try this stuff, and then they end up ditching labels because, it doesn't actually work to keep it updated. It's way more work to actually try to keep it updated, but then you always end up in this world where the data is stale and now you can't trust the labels, but the labels are there. And so you might as well just not have the labels. And so finally what happens, this happens like basically every time with dynamic languages, and this is why we're simulating it in Wire World, is that you're eventually going to need to upgrade the wires to use type guards so they don't let stuff they don't expect in. And so this is going to actually work pretty well. What you're going to do is, at the ends of the wires, you're going to say, this is an electric wire, and you add this thing on it, and it's going to check anything that comes in to make sure it's electricity. If it's electricity, it works as expected. If it's not, it's going to be like, shut down the wire so that it doesn't kill itself, basically. Now, the problem with this is that it does cost a little bit more to get. It's probably going to take some work to install. And now, the throughput of your wire is not as high because it's checking everything that goes through it. And so there's now overhead for every item, every payload that goes through it. And again, in programming world, this is going to be very much like a null check. You're checking every single thing that comes in to see if it's null. And it's not that big of a check, but it is an extra check that you have to do every single time on every single item. And so at scale across hundreds, thousands, millions of wires, it does add up. But the good thing is, that this does work pretty well. We're preventing a lot of these fires and these nasties because we're not allowing these wires to cross, really. If they were about to cross, it'll just turn off and not do anything. And so we have a lot less fires, a lot less nasties. Now, the one downside to this is that we sometimes don't realize that we've connected the bad wires together until we get a downstream complaint from a customer. And so this is going to be something like the customer is like, why is my water not working? And you're like, I don't know. I installed that last week. Why is it not working? And you go back and you're like, we connected this to the electricity instead of the water. Or it's going to be like the sewage just stopped up or the power is not on. And so we're not getting the fires anymore. So it's better than the fires. It's better than, the sewage entering the water stream. But because we don't get that immediate feedback, we only get it when it hits the customer. One, the customer has a bad time. But two, we have a bad time because now we got to go back and, dismantle the wall and see what happened and then go fix it and then go fix the wall again. And so it's a bunch of rework for something that we believed we had already finished. And now let's look at the version where we go to type-safe wires. And this is what that diagram above looks like with type-safe. A little bit easier to read. We've got little bathrooms here. We've got our desks or whatever here and here. Maybe we got a little kitchenette here. A little bit easier to read with these colored wires because we know what's going on in there. Now with type safety, with these type-safe wires, we actually avoid all the fires and nasties altogether. We skip directly to the type guard phase, but with an upgraded version. And this version is built in by default, so we don't have to do any custom work to remember to add this stuff on to each end of the wire. It does not lower the payload throughput because we aren't checking everything that comes through. We just know that the connectors will not connect to things it doesn't connect. And this is what we call like a free abstraction, if you will. Nothing's free, but pretty free. And the next one is that it's actually impossible to connect wrong. And so that issue with the type guards where we can actually still connect them wrong, and we won't find out till later, our type-safe wires won't let us to connect at all. And so we get immediate feedback that this won't work. We need to figure out another way. And of course, we're still making changes at about 10 per day. We have the same change velocity, but most of these changes are going to be things that we're choosing to do. We're not getting pulled into urgent fires or nasties that we need to put out or fix. And instead, we can make forward progress on whatever it is that we wanted. And the one issue that often gets called out for these type-safe wires, for type-safe programming in general, is that it might sometimes take longer to make these changes. You might realize that you don't have the correct color wire where you need it when you first start building, and thus you need to do more wiring before you call a project done. But interestingly, if you were to basically time the project from start to finish being start to it actually works correctly, including all the firefighting and rework you had to do for it to actually work correctly, not just, be done in Jira, it's actually going to be much lower because there is less rework and thus less overhead, context switching, firefighting, remediation, stuff like that, because you did it right the first time. And so the outcome here at this scale is that type-safe wires actually win by a long shot. And what's interesting is we can actually see that the dynamic wire slowly started band-aiding itself with solutions to try and solve the issue of not understanding what's in the wire because it costs so much in the form of firefighting and rework. So again, it feels faster at the beginning, but then actually the rework, the firefighting, makes it take way, way longer. And eventually, you and your org will catch on to this. And so you'll start trying to find solution. And if you kind of combine all of the things that they were doing to try to solve for this type safety issue in dynamic wires, really what they end up doing is approximating versions of what type safe wires provide. So they're trying to prevent bad inputs entirely. They're trying to make it easy to understand the wires with the labels or the dot comments. But the problem is you're not able to fully catch up to what a type-safe native wire provides. You can't quite add the dot comments onto the entire flow of that data. Yes, you're preventing the bad inputs, but you're adding runtime cost to actually do that via type guards. It just can't quite stack up to native type safety. And I want to stop here because, this is complex, this is very long, very abstract. And this might seem too fantastical and abstract, but this really does happen in programming and orgs all the time. And the general way this works is that, dynamic languages may seem like a speed boost at the start, but they always, and I really do mean always, end up being a speed hindrance sooner rather than later, at the point where individual engineers cannot keep an up-to-date mental model of the state of the codebase, the state of the program, due to the codebase's size, times the number of changes that are happening every single day, and thus makes their old mental model out of date enough to cause problems. And in my experience, this typically becomes obvious at around 2 teams of people or 10 engineers and only gets worse from there. Okay, scenario 3, last scenario, I promise. And this is going to be taking it up one more level of scale, one more magnitude. We're going to be wiring an office building. And so where previously we did, 1 floor, now we're going to be doing 10 floors. And so we're going to say that the wires now are up to 100,000. We're going to say that we've got 100 engineers. So we're just 10 timesing most things. Wires gets a little bit bigger due to the power of time, basically. Some things do stay static in software, so you slowly actually get a larger ball of code. So we're at to 100,000 wires. 100 changes a day. And this is going to be similar to a software product at a mid-sized company. So we're kind of mid-sized, yeah. And not even like large mid-sized, like we're just mid-sized. So we've already been through the main differences in practice between dynamic and type-safe wires in scenario 2. So I don't want to go over that again. I think we understand it by now. But what I do want to point out is that by going a step further in scale, we actually make these problems increase in magnitude. And this is for a few reasons. So the first is that the speed of changes and the size of mental model is going to only continue to grow. And this is because over time we're building more and more software, and some of that software can stay the same, but we're building more. So the actual volume of the software and critically the surface area of change gets much larger as time goes on. But also typically as a company grows, we're getting more engineers. And so now we're making more changes at once. And so now these things are compounding to make it harder and harder to get a full mental model of what the software is doing. And eventually what this ends up doing is it literally makes it impossible for anyone to have a full understanding of the full system in their head. And honestly, this is a very dangerous thing to believe you do have a full understanding, because at the end of the day, you don't. The next, and one I kind of touched on, is that the surface area of potential breakage grows exponentially. And so, as our volume of software is growing, as our surface area of change is growing, everything is interconnected. And so if any one of these breaks because, for whatever reason it breaks, it has the possibility to break everything. And so that means as our surface area of change grows, the possibility that we're about to crash the whole thing actually grows as well. One bad sewage wire leading into our water wire anywhere in the system now pollutes the water wire for everyone downstream. You can think of it like a city, like the river floods way upstream, and that actually is causing, overflows of something down here, and now you can't drink your water because it's polluted or whatever. That's the kind of thing that happens in software as well. And finally, let's say we're dealing with this, we're dealing with the mental model thing, we're dealing with it, but we also have to deal with people turnover at this scale, right? We're dealing with people at the end of the day. And so your most experienced and knowledgeable people, let's say you have 100 of super knowledgeable people, they've been here since the beginning, they probably know the ins and outs of the building and the changes and the history, so they can kind of keep up with some of this stuff. But that's not what your team's going to look like, right? The most knowledgeable people are going to be leaving because they've been there 4 years, they're bored, they want to do something else. And so now you're going to have to be getting all these new people that have zero context the way you're doing things. So if everything's stuck together with duct tape and, there's warning signs everywhere to not do stuff, guess what? They're going to break the warnings, the duct tape's going to come off, and everything's going to fall down. And so you have to figure out ways to build a scalable onboarding process to make new people productive quickly. And that basically means not doing this clever stuff that only, the experts can understand. And I want to stress that we are not even at a large company or piece of software yet. And we're definitely not at planet scale. And yet we're running into issues with the biggest bottleneck in software development, which is humans. And so, this is basically what the office building looks like, a medium-sized company, piece of software. Each of these is kind of the office floor or office units we looked at earlier. And now we've got to deal with all this stuff. Easy to see that this is confusing already, but here's the water. If I put the sewage in the water, I corrupt everything. And that's just how software works. And so we're looking at this and we're like, this is infeasible. This is ridiculous. Like, there's no way it works that way. And I agree. There has to be a better way to prevent engineers from making small, unintentional, and catastrophic mistakes without needing them to understand the entire blueprint of this thing, which again, we talked about is impossible, or learning our history of custom fixes, which again is very inefficient. Onboarding would be ridiculous if everything was custom and hard to understand. Or just learning through trial by fire by, connecting the sewage to the water and realizing that's not where you're supposed to work because that's dangerous, it's bad for your business, and it's honestly demoralizing for the person because they didn't mean to do that. And the answer, of course, is if only we had a wire that was easy to understand by anybody, whether they're an expert or new, that is immune to doing these very catastrophic, easy to make wire crossing issues and could scale up to the next 100 changes per days or engineers or office buildings, and ideally the next 1,000 after that. Because that is what you need to do by the time you're large scale or planet scale. You have thousands, tens of thousands of engineers. You got to be able to withstand this. And I don't know, this is still complex, but at least it's easier to read. And at least I can't cross the electricity with the water or the sewage with the water or anything like that. And the truth is that the outcome is really that type-safe wires are the only ones that work. I believe this logically, I believe this theoretically, and I've seen it happen to so many companies. Instagram moved to typed Instagram. They built their own linter for type checking. Rippling's moving to type-safe Python, ripping things out and writing it in Java and Go to get better types. Reddit called bankruptcy on their own Python monolith because they couldn't do types well enough. They're moving to Golang for types. At the end of the day, we got to solve for humans, and at the end of the day, you got to use types. That's it. It's the only one that works, and it's the only one that scales. Next. So yeah, this is way longer than I thought it would be, and I did go through several drafts of this, trying to make it, more accurate, more relatable, shorter, so I could try to, objectively compare dynamic and type-safe approaches in the wild. And, I think I still ended up way longer than I thought, and definitely a bit hot on dynamic, but truly dynamic languages are a dumpster fire at scale. So, maybe this is appropriate. I'd love to know if this was helpful or relatable or useful in any way, or if you think I'm wrong, or if this is too confusing. That feedback really helps me to iterate on this argument, the metaphor, to try and make it a little bit more understandable, a little bit more objective, so we can kind of end up on the simple scalable system. What is the actual outcome of this? And also let me know if you have any ideas or suggestions for other concepts or deep dives like this that you'd like explored. If you like this post, you might also like the HAM stack, a simple scalable tech stack for building modern web apps fast and cheap, or why you should choose HTMX for your next based or web-based side project and ditch the crufty multi-page application and complex single-page application. And finally, if you're into metaphors, you might be into servers as factories, a simple metaphor for thinking about web servers. That's it for this video. Thanks for watching, and I'll see you in the next one.